So we've talked about power series. We're now going to discuss Taylor and Maclaurin series. And yes, they are similar to the Taylor polynomials and Maclaurin polynomials that we've talked about already. So the Taylor polynomial was an approximation to a function at some point c that took on the form fc plus f prime c times x minus c plus the second derivative of f at c divided by 2 factorial times x minus c squared, and you would do this till you have the nth term. And the result was a polynomial that was what we called the nth order approximation to some function f. We are going to take this notion and we are going to extend it so that it is not only a polynomial, but it is now a power series. Instead of taking an approximation only to the nth degree, we are going to take a power series and try to make our what was an approximation now as exact as possible. So this power series is called the Taylor series of f about c, and if c is equal to 0, we're going to have, again, the term Maclaurin series used instead. So the following is a list of Maclaurin series and their intervals of convergence. Now, this interval of convergence is really important, just the same as with the Taylor, the Maclaurin polynomials that we used before. You are expected to memorize and know each of these Maclaurin series. They're no different from the polynomials. The only thing you need to remember is that it's the sum of all infinitely many terms together. So that's really the only difference. If you knew your Maclaurin polynomials already, which you should, then all of this should be familiar to you already. The new one might be this arctangent x here and the intervals of convergence. So those are the additional things that you need to remember when it comes to this chart of, Maclaurin series that you must know. So this series here means, the fact that the interval of convergence is all of R for these three series here, try to say that 3 times fast, means that this series actually describes e to the x for any value x. If you were to try and figure out what let's say we wanted to know what the value of e to the power of pi was. Well, if you wanted to figure out e to the pi, what this value is, all you would need to do is compute this power series here. Oh, that should be a 2. Plus pi cubed over 3 factorial plus factorial plus ... This power series or Maclaurin series here describes this value of e to the pi perfectly. This series here will converge to this value. That is what this interval of convergence means. For this one here, for this geometric series here, so long as the absolute value of x is less than 1, no matter what number you pick for x that satisfies that condition, it will converge to this function here. So that's really, really important. And then we have the Maclaurin series for ln x and arctangent x. Arctangent x might be new to you, but how to figure it out is not is a method that you already know how to do. Arctangent x has the derivative of arctangent x is 1 over 1 plus x squared. So this is the derivative of arctangent x. This has a power series very similar to this. In fact, the power series, I'm just going to write it here, is minus x squared to the n, and you sum from n equals 0 to infinity. You take this Maclaurin series here, and then you modify this minus x part so that it becomes plus x squared instead, and then you modify the power series here appropriately, which is what you get here. Now, if you integrate this term by term, you will, in fact, get this arctangent series here. So this becomes minus 1 to the n x to the 2n, right? If I simplify this, summation n equals 0 to infinity. If I integrate x to the 2n, you get x to the 2n plus 1 divided by 2n plus 1. And lo and behold, that's exactly what you have term by term for the power series of arctangent x. That's because, as we've talked previously in the last videos, integrating a power series as long as you're on the interval of convergence, allows you to integrate the power series term by term, and then whatever that power series converges to function-wise, the integral of the power series will converge to the integral of the function itself, which is exactly what you have here. So that was a little messy. But that's how you find out the Maclaurin series for arctangent. And if you have any other functions whose power series that you're trying to find, you want to do so in a similar fashion. You want to modify the known Maclaurin series into Maclaurin series for new functions, similar to what you may have done for Taylor polynomials and Maclaurin polynomials instead.